Good morning, children. Today we will discuss about sampling theorem. Let us go with the presentation. Sampling theory or sampling theorem. So here it is the process of converting continuous time signal into discrete signal. So that is here it is a process of converting continuous time signal into discrete signal. So here we have to reconstruct the original signal. So how we have to reconstruct the original signal here? So for that we need here we have to consider sufficient number of samples. That means it depends upon so how many samples we have to take. So it depends upon the number of samples to be taken depends upon the maximum signal frequency present in the signal. That means here maximum signal frequency represents with fm. So maximum signal frequency. So a number of samples to be taken depends upon the maximum signal frequency which is present in the signal. That means here we have different types of samples. So ideal samples, natural samples, flat top samples. Now here today we'll discuss about sampling theorem. Now what is the statement of sampling theorem? So based on the time and frequency. So it depends upon the time and frequency. So sampling theorem it depends upon it based on the time and frequency. So here if we consider a band is limited signal of finite energy which has no frequency component higher than frequency. That means which is represents in H. So which is completely described by its sample values at uniform intervals less than or equal to 1 by 2 fm. That means here it depends, it is based sampling theorem which is based on the time and frequency. So here we have to consider, so here what is the statement of the sample theorem, which is it is a band limited signal of finite energy which has no frequency component higher than the frequency which is completely described by its sample values at uniform intervals less than or equal to 1 by 2 fm. That means here this is Ts which is less than or equal to 1 by 2 fm. Here fm represents the maximum frequency. So here the statement of sampling theorem simply it describes Ts. Here what is Ts? Here the time period of the samples. Ts it is time period of samples which is less than or equal to the 1 by 2 fm. So so a band limited signal of finite energy which has no frequency components higher than the frequency which is higher than fm, which is which may be completely recovered from the knowledge of its samples taken at the rate of 2 fm samples per second. That means here the statement which gives us here fs is greater than or equals to 2 fm. So here what is fs? Here it is rate of sampling. So fs it is rate of sampling which is greater than or equals to 2 fm. So here fm it is the maximum frequency of the original signal, or fs which is equals to 1 by ts. So here we have ts is less than or equals to 1 by 2 fm, or fs which is equals to 1 by ts, or fs it is greater than or equals to 2 fm. So here fs it is the rate of sampling which is greater than or equals to 2 fm. So here the statement which gives us the which tells us here fs which is, and that means rate of sampling which is greater than or equals to 2 fm. So here fm it is the maximum frequency of the original signal, and here so here this is the original signal, this is original signal, and here these are the samples, number of samples here, and here the distance between each sample. So sample to sample here it is duration between two samples which is ts, and already I told you fs equals to 1 by ts. fs equals fs equals to 1 by ts. So here this one duration between two samples it is ts, and here according to the statement of this sample, that means which is based on the time and frequency. So here's ts, that means duration between two samples ts which is less than or equals to 1 by 2 fm. And here we this one second one, so this statement here fs equals to 1 by ts, where ts equals to 1 by 2 fn. So here ts is nothing but duration between two samples, and here fs is nothing but rate of sampling, and FM it is the maximum frequency of the original signal. So here this is the sampling, and here this line represents the original signal, and here these are the samples, and the duration between two samples which is represented with Ts, and the distance duration between two samples is Ts, and Fs equals to rate of frequency equals to 1 by Ts. So Fx equals to 1 by Ts. Now let us consider here. So if signal is band limited to Fm, then x of omega equals to 0. If omega is greater than omega m. So here omega it is a frequency here. If signal is band limited to the Fm, that means here Fm it is the maximum frequency, then x of omega equals to 0. So here we can see. So if signal band limited to Fm, then x of omega which is equals to 0 only if omega is greater than omega m. So let us see. So this is the uh, this is this is the time axis, and here this is x of t, and here this is the signal which is varying with respect to time. This is the signal varying with respect to time, and here we can consider here this is the center line. It is 0, and here this is frequency line, and here this is and here it is omega m. So left side negative value minus omega m. So here x of omega equals to 0. That means signal band limited to the maximum frequency, then x of omega equals to 0, and the condition of omega is greater than omega m. Now let us consider the pulse train. So this is the actual signal, and here this is the frequency x of omega at 0 when the signal band is limited to the maximum frequency. And now let us consider the pulse train. So these are the pulses which are arranged like train. So that's why here we are saying these are pulse train. And here we have the center line, it is 0, and Ts, 2Ts, positive values, 2Ts, 3Ts, 4Ts, 5Ts, and so on. And negative values, minus Ts, minus 2Ts, minus 3Ts, and so on. So mathematically we can represent this pulse train as delta Ts of t, which is equals to 1 by Ts, 1 plus 2 cos omega st plus 2 cos 2 omega st plus 2 cos 3 omega st plus so on. So like this we can represent mathematically the pulse train. So this is the actual signal which is varying with respect to time, and here this is if signal is band limited to the Fm, then x of omega equals to 0, and here this is omega axis, and here we have seen this time axis, and this is pulse train. Now let us consider for sampling. Let us see the input which we have to multiply x of t with this one pulse train delta Ts of t. So let us consider the input x of t delta Ts of t. So by using multiplier, so this is the input, and by multiplying these two we will obtain output g of t equals to x of t into delta Ts into t. So x of t delta Ts already we have this value. Let us substitute this value as it is. So this 1 by Ts into 1 plus 2 cos omega st plus 2 cos 2 omega st plus 2 omega s 3 omega st plus so on. So this is the output. So for sampling, so by we are here we are using multiplier. So by multiplying the input signals, that these two x of t with delta Ts. So here delta Ts of t, which is pulse train. So this is actual original signal. So message signal. So here we will obtain output g of t equals to x of t delta Ts into t. Now let us see this one. So output samples. So here we have seen this is the input, and this is also input. So by multiplying these two, we will obtain the output like this. This is the original signal, and here these are the pulses or samples. So this is the dotted line, it is input. So output g of t samples. So this is the, so here in frequency domain g of omega. So here we have 0, Ts, 2 Ts, 3 Ts, and so on. So left side we have minus Ts, minus 2 Ts, minus 3 Ts, and so on. So here in frequency domain, g of omega equals to 1 by Ts into x of omega plus x omega minus x of omega minus omega s plus x of omega plus omega s plus x of omega minus 2 omega s plus x of omega plus 2 omega s. So like this, we have to consider in frequency domain, we have considered g of omega. That means we are including here omega. So this is how we have write in frequency domain g of omega equals to 1 by ts into x of omega plus x of omega minus omega s plus x of omega plus omega s plus x of omega minus 2 omega s plus x of omega plus 2 omega plus so on. So this is the output. So by multiplying these two, we'll obtain the output, this one. This is for sampling, this is the output. And here this is how we represented in frequency domain. This is so actually the output here by multiplying x of t into delta ts of t, we'll obtain this one. And in frequency domain, just we are multiplying with omega, we are considering, and 1 by ts it is as it is. So here x of t, and we are replacing here with omega, x of omega plus x of omega minus omega s. This is how we have to consider. And this is by considering, that means here this is the samples with respect to, now let us consider this frequency axis here. So here this is 0, and right side omega m, omega s, 2 omega s, and left side negative values minus omega m. Here I have forgotten negative, minus omega s, minus 2 omega s, and here this is g omega. So here this is g omega, and here if you consider in frequency domain, we have x of omega, and this one x of omega minus omega s plus x of omega plus omega s, and this is the third term. And here we can see here this is first term, this is x of omega, and here this is g of omega, and the second term x of omega minus omega s, this one at omega s center line it is omega s, and this is for this one x of omega minus omega s plus x of omega plus omega s, and the third term this one x of omega minus 2 omega s plus x of omega plus 2 omega s. So this one, this represents here. And here when we by passing the signal with low frequency low pass filters, by passing the signal with the low pass filter, here LPF, low pass filter, so we can extract the original signal. So by passing LPF, we can extract the original signal. And here we have the samples with respect to 0, with respect to omega m, with respect to omega s, with respect to 2 omega s, and so on. And here we get only if we have the condition omega s is greater than 2 omega m. So here whenever we have the condition to omega s is greater than 2 omega m, then only when the samples here we have considered with respect to 0 or with respect to omega s, 2 omega s, and so on. So by passing the low pass filter, we will extract the original signal. So this is how we can represent. Now let us discuss. So as long as Fs is greater than 2 Fm, g omega will repeat periodically without overlapping. Let us see. So here, total here we have three conditions. So let us see first one here. So as long as Fs is greater than 2 Fm, g omega will repeat periodically without overlapping. So spectrum g of omega extends up to infinity frequency, but purpose is to extract the original spectrum x of omega out of the spectrum g of omega. Already we have seen. So here we have extracted the original signal here by using the condition omega s is greater than 2 omega m and fs is greater than 2 fm, we will repeat periodically without overlapping. So we will see. So at receiver place, low by using the low pass filters of frequency omega m, so we can extract the original information. And here we have three conditions or three stages. Here we have fs is greater than 2 fm, fs equals to 2 fm, fs is less than 2 fm. So what will happen when these the conditions when we apply? So to avoid the successive cycles not to overlap, we have to consider this condition fs is greater than 2 fm. That means the signals which we are received without overlapping and successive cycles just touch each other, fs equals to 2 fm, and successive cycles overlap each other, not overlap, overlap. So not overlap means greater than 2 fm fs and less than 2 fm we consider it overlap each other. So reconstruction, we will obtain the reconstruction without distortion. So this is the condition: Fs is greater than or equals to 2Fm. So Fs is greater than or equals. So by using these two, we can reconstruct the original signal without any distortion. So not this one. So by using these two, so Fs is greater than or equals to 2Fm. That means without overlapping, and just they touch each other. So by using these two, we can reconstruct the original signal without any distortions. So Fs equals to 2Fm. So hence Fs is referred as Nyquist rate. So if you consider Fs which is equals to 2Fm, so Fs is referred as Nyquist rate, and Ts equals to 1 by 2Fm. First one, in the initial we have considered Ts equals to 1 by 2Fm. So Ts, it is Nyquist interval. So these are the conditions. When these conditions, so here Fs and Ts, these are, so here Fs it is a Nyquist rate, Ts it is a Nyquist interval. That means Ts equals to 1 by 2Fm. If this one, so Ts is Nyquist interval. So Fs equals to 2Fm means here Fs it is referred as Nyquist rate. Now let us see. So this is the final figure. So let us consider the first figure. Fs is greater than 2Fm. So no overlapping. So here this is 0. This is omega s, 2 omega s, minus omega s, minus 2 omega s. So like this we will obtain. This is the frequency axis here. So if we consider the case Fs is greater than 2Fm, we will obtain without overlapping. So second case, so already we have considered here this one. So second one we have Fs equals to 2Fm. That means the here Fs equals to 2Fm means successive cycles just touch each other. So just the cycles just touch each other. That means like this we'll obtain like this. That means already we have first one. So second one just they touch each other. So here Fs it is a Nyquist sampling just touching, and last one we have Fs is less than 2Fm overlapping. So here the cycles are overlap. So this is how we will obtain the final one. So these are the three stages. So first one not overlapping, touching, overlapping. So finally we can observe here. So this is the region where the overlapping. So here we can observe the overlapping. So this is about the sampling theorem. Thank you, children.